All right, ladies and gentlemen, welcome back to another video with Mr. Kenton in AP Chemistry. We're moving right along here in Unit 5, and we've gotten to kind of our next big thing with mechanisms and rate laws, which College Board AP, they refer to as steady state approximations. And I mean, just real briefly, to remember, what this means is that how do we deal with mechanisms where a rate law is proposed, but it includes something that isn't a part of your overall reaction, right? So what do we do when we get a mechanism where, let's say, an intermediate happens to be part of our rate law or our rate expression based on the slow step or the rate determining step? That's what we're going to be looking at today. How do we approach problems like that? Can we even have that? So let's dive in. Let's take a look at what this looks like. So, I mean, it's just going to start off with just looking at an example. That's really what we're going to take a look at, right? So let's say that we're told we have the following reaction. We've got 2 nitrogen monoxide plus bromine produces 2 moles of NOBr, right? There is the reaction. And we're told that the experimentally determined rate law, so you have experimental data, you carried this reaction out, and you determined that the rate equals K times NO squared times Br2. So it's second order with respect to nitrogen monoxide, and it's first order with respect to bromine, right? So you've got that information, and you're given a mechanism. You're saying, all right, consider the following mechanism, right? And you're given this. You're told, all right, nitrogen monoxide plus Br2 is in equilibrium with NOBr2. And then in step 2, you've got NOBr2 plus nitrogen monoxide makes 2 NOBr. And, you know, common question, we see this mechanism. The first thing we ought to go to is say, okay, what's my rate determining step, right? What's my slow step? And we see that, and we see that it's step number 2, right? Step number 2 is most definitely our slow step, right? And so because we understand the things that we've learned previously, we can then look at that and we say, okay, my rate law then is going to be K times NOBr2 times NO, which at first glance, that doesn't look like our experimentally determined rate law, right? And so we see that, and we've got that K2 times NOBr2 times NO. But something I want to draw to our attention is that notice that in the rate law, what we've done is we've said, okay, we look at here and here, we see that NOBr2, that's an intermediate. Right? So then the question was, okay, can we even have an intermediate in our rate law? Because initially we look at this and we're like, slow step and the experimentally determined rate law, they're not matching up. And we might think, I don't think this mechanism supports the particular experimentally determined rate law. Well, there's 2 things we got to account for, right? First, we have to deal with this intermediate. Can we even have that in our rate law? And the short answer to that is no. We can't have an intermediate be part of our rate determining step. And we'll get into kind of the reasons for that on the next slide, right? And so, like I said, the problem is we're saying the rate law is dependent on an intermediate. And that's problematic because what we see is that intermediates are usually very unstable, or we also see that they have lower unknown concentrations. And so if you start looking at rate data is pretty dependent on having consistent or really measurable concentrations. Well, if you have something that has a low or an unknown concentration, you can't make an experimental decision based off of that. So what we've got to figure out to do is we need to find a way to remove this intermediate from our rate law. And that's where this steady state approximation term that we see in the curriculum comes from, right? It's our ability to say, okay, this is how we're going to remove an intermediate from our rate law by looking at what we call a steady state approximation. It has to do with equilibrium, right? And so what we're going to need to do is we need to express NOBR2 in terms of the NO and BR2, right? That should say NO and BR, not NOBR and BR2, right? So let's just kind of ignore that BR that's right there. And we have to assume, well, we don't have to assume because they told us in step 1 that it's at equilibrium, right? And so we saw those forward and reverse arrows, and at equilibrium, what that means when you start looking at it from a rate perspective, right? It means that the forward rate is equal to the reverse rate. Now, let's be clear here. I'm saying that the rates are equal. I'm not saying that the rate constants are equal, right? So the rate constants are not equal, but the rates, like the numerical value for the rate, should be the same going forward as it is going in reverse because it's at equilibrium. That's one of the key components of what makes something be at equilibrium. All right, so what we can see here then is we've got that step 1 where we can make this steady state approximation. We're going to try to make this substitution to remove NOBR2 from our theoretical rate law, right? And it's going to involve us using step 1 and setting up a rate law that's setting those two rate laws equal to each other, right? Hopefully you're tracking with that. Take a look at the next slide. Feel free to pause this video if I'm going too fast. So we can ignore the bullet that's kind of below right now. Let's focus on the top. So by a definition of equilibrium, the rate law that we get for the first step is going to be that the rate rate 1 or rate forward equals rate reverse. You could think of it as R1 versus R negative 1. So you've got K1 times concentration of NO times BR2 equals the rate constant of the reverse times the concentration of NOBR2. Now, if you guys are following along with me here, you could think of this algebraically, right? We can isolate the term NOBR2 to get it by itself by simply dividing by the rate constant of the reverse process. Now, when we do that, what we end up with is we say that concentration of NOBR2 is going to be equal to the following term, right? K1 over K negative 1 times the concentration of NO times the concentration of BR2, right? So now we've isolated, we said, okay, this is what NOBR2 is equal to based on our equilibrium step. Now what we can do is we say, okay, I now have a term that was an intermediate that I can remove, and I can put it in terms of things that I'm actually seeing in the overall chemical process. So when we do that, we would get a rate where you would get K2 times NOBR2 times NO. We're going to make that substitution. And we're going to end up with K2 times K1 divided by K negative 1 times concentration of NO times BR2 times the concentration of NO, right? Now again, remember these K values, they're not all the same, but when you multiply and then divide constants by each other, you're still left with a constant, right? And so ultimately we can simplify all of our K terms to simply just a K, right? So we combine everything and we get that the rate equals K times the concentration of NO squared times the concentration of BR2. So we're showing now with our theoretical rate law that the rate is second order with respect to NO and first order with respect to BR2. This now matches our experimentally determined rate law. All right, so even though initially we looked at it and it was like, no, this doesn't match up with our experimentally determined rate law, this does in fact support it. Remember, it doesn't prove it, but it does support our mechanism. It does show us that, hey, if this reaction takes place, this is a possibility for how that's going to occur, right? So this mechanism supports the rate law, the experimentally determined rate law, but it doesn't prove the experimentally determined rate law. All right. So to recap what we did here, right, with steady state approximations, it helps us deal with a situation where, let's say, an intermediate happens to be included in your rate determining step, right? Now, the way for this to function is you have to have a step that is in equilibrium, right? And by equilibrium, what we're focusing in on here is simply stating that the forward and reverse rates are the same. Now, that doesn't mean that the rate constants are the same. It just means that their rates have to be equal to each other. And so because they're equal to each other, we can set up an algebraic expression where we can solve our intermediate for something that's in terms of what's in our overall process. And you can do that, make the substitutions, combine all your terms, and you would get a new rate law that no longer has your intermediate, and you could use that new rate law to check it with the experimental rate law. Okay, I hope this makes sense. If you do have any questions, please do not hesitate to ask. Bring them to office hours, fill out the Google form, type in your questions there, and I'll do the best I can to assist you there. Thank you guys for stopping by, and I look forward to seeing you guys again soon. Take care.